In this section, we're going to be looking at hypothesis testing for means, or significance tests for means. So just like we saw with proportions, we're going to see that we have a null and alternative hypothesis that we're going to be able to write. However, since we're working with means, the main symbol we're going to be using is mu. We also have that the same conditions, those independent, random, and large enough conditions are going to be remaining the same. The method we're going to learn is back to using the t distribution. It's a one sample t test. And why is it t is, again, when we're working with means, we'll find out that, again, we don't have the population standard deviation. So we have to rely on the less precise distribution of the t distribution. And so you'll see everything is basically the same. We'll calculate a test statistic, calculate a p-value, and then interpret that in context. So as a quick reminder about those t versus z type of inference procedures that we're learning, whenever we're working with proportions, or p, that's when we have categorical data, we're looking at a sample proportion. Which, remember, the symbol for that is p hat as our piece of data. That's as our statistic. When we're looking at means, mu, and we're trying to estimate that, what are we going to use is our sample mean, which is x bar. And we use this for quantitative data. So the key thing, the difference on why we're going to be using z and t, again, is for means, we have that the standard deviation of the population is almost always unknown. Right? We don't know what that is. We only have the sample data. However, on the other hand, when we're working with our proportions, the standard deviation of the population is actually calculated based off of p. So we can actually know this. It is known. And so we are able to use the normal distribution versus in the other one where it's unknown and we have this random variable s that we're using instead, we have to use the t distribution. So going through this, you'll see again, it's basically the exact same thing. In fact, these notes should look just like the last set of notes from proportions, which we have the same 5 steps: defining our parameter and hypotheses, naming our test, checking our IRL requirements, calculating the test statistic and p-value, and then finally interpreting those in a sentence or 2 sentences. And the way we write our hypotheses are the same. We have our h naught, which is this h0 on there. We say h naught. And remember, the null hypothesis always has an equal sign. We also have the alternative hypothesis, ha, which again sometimes you'll see as h1. And those always have an inequality to it. So let's just jump straight into an example of writing these hypotheses. So here we have, from data collected this year about the number of years of service an employee has at retirement within a large company, we obtained summary statistics. So these are statistics here from our sample. Test the claim that the mean number of years at service at retirement is 25 years. So there's our claim right there. This is what we're trying to see. Is this true or is it not true? Well, we have to write our null and our alternative. So remember, we're talking about a mean number of years, so this is mu that we're comparing. And the claim is right there, it's 25. So we're going to make sure that we assume that is true. So if we're saying it's 25, then okay, I will believe you. We'll say it's 25. Now what are we trying to show, though, is that it's whether or not this is true. It doesn't say if we care if it's longer or shorter. So we're still comparing the 25, but since I don't care about the direction, we're just going to put a not equal to there. And there we go. We have our null and alternative hypotheses. The only difference now is we're going to be using mu instead of p. Let's look at one more. The run time for 20 participants at a local 5K race was x bar equals 29.2 minutes with a standard deviation of 5.67. So notice these numbers that are given to us are the statistics. That's not what we're assuming. That's what we actually collected. But what are we actually trying to test? Is there evidence that the true mean runtime for all the participants is below 30 minutes? So see if you can try and write your null and alternative hypotheses. And then pause this for a second to see if you can write it before you copy my answer. Hopefully you have something written down. And since we're comparing it to 30 minutes, then 30 is what we're going to assume. And we're trying to show specifically that we're below 30 minutes for the mean, so we'll put a less than 30 here. So there you go, writing our hypotheses. That's one difference. The second difference is our calculations. We are going to be finding a test statistic, but remember, it's very much the same. It's like a standardized z-score in a sense, but now we're going to call it a t-score since we don't know our sigma, so we don't know the exact standard deviation. But it's basically the same. We're going to subtract our parameter, divide by the standard error, the standard deviation of our statistic, or at least an estimate thereof since we're using S. But it looks the same. Our statistic is our piece of data that we're going to be using, or the value of our score that we're using. The parameter is from our null hypothesis, mu naught. And then our standard error is just, again, the same thing that we saw from before. It's our standard deviation of the population, or in this case, our sample, since we don't know the population, divided by the square root of n. So it comes out to this formula for our standardized test statistic for a t-test. So let's practice writing those out. So if we have these hypotheses over here on the left, and then we have these observed statistics, well, we can just find our t-score. What did we get was 36. So we have 36 minus the hypothesis. Well, actually, let's write down the formula first so you can match it up. We have our score, which is our statistic, minus the mean from our null hypothesis, divided by S over the square root of n. So our score was 36 minus the null hypothesis mean, which is 40. We're assuming it's 40. And now we have S, which is 3 over the square root of 20. Now just be careful on how you type this into your calculator. If you need to, put parentheses around the top and bottom so that way you can keep it together. Or you can just do them separately and just make sure you don't round off too many decimal places. So working this out, we get t is equal to negative 4 on top over 3 over the square root of 20. And if we just type this into our calculator, we end up with negative 3.329. And for t-scores, we typically round to 3 decimal places. Why don't you try part B, see if you can get the same answer as me. So you can pause it and try it out. And you should be getting 14.142, which is actually a very big t-value. I would always double check that if we ever get something this big, because again, we would probably expect something to be a lot closer than that. All right, let's now apply this to an actual 5-step problem. So we're going to take that run example again, and let's actually perform our full 5 steps, defining our hypotheses, naming the test, checking the requirements, and then doing the calculations and interpreting. So step 1, well, let's make sure we understand the problem. The run times for 20 participants at a local 5K race was a mean of 29.2 minutes with a standard deviation of 5.67 minutes. Is there evidence that the true mean run time is below 30 minutes? So step 1, we actually already did earlier, was writing our hypotheses. And we wrote that, okay, we're going to believe it's 30 minutes right now, and we're trying to find evidence that it's, again, below 30 minutes, where mu represents the true mean runtime for all of these participants. So what are we going to use to find this, or test this claim, is we're going to use a one-sample t-test. So again, it's t because we're working with means. So let's check our requirements. So we have our independent, random, and large enough. So we need 20 to be less than 5% of the population, so of all runners. Now this is just a local 5K race, so this one's kind of tough to believe. We're going to make the assumption though, but we do need, let's see, if we need 20% of all 5% of all runners, that's like 400 runners, which is possible for a local race, but that may be kind of tough. So we're not sure if this one's satisfied. What about random? It actually doesn't state. So this one is also kind of failing. Not necessarily random. What about large enough? This one also looks like it fails as well, because we have only 20. And remember, for means, we need at least 30, and since we're smaller than that, we fail that one. So we're going to go through this. We don't know what the population time looks like, but it's probably going to be skewed. But we're going to go through this anyway, even though we failed all these. Just again, we have to make sure we understand that our results are probably not going to be the most accurate. So let's take a look at step 4, because really we're just going through this to make sure we can understand these steps and these processes. So step 4 is we need to find our test statistic. Well, we just practiced that. Let's find all these pieces of information we need to use. So we have X bar is 29.2. S is 5.67. N was 20. And we also have our null hypothesis already written out here. So if we're doing our formula, this would just be 29.2 minus our mean from our null hypothesis divided by S over the square root of N. And just typing this into our calculator gives us 0.631, and that's negative. So we are about 0.631 below the 30 minutes. So what's the other thing we need to calculate in this point? Is our p-value. So our p-value is going to be equal to, we're only looking at one of these sides. So we're looking at the less than side, and we have negative 0.631, and we want to find the probability of getting that or lower. So let's go over to StatCrunch, our calculator, or you can use a table if you want, but I'll use the StatCrunch calculator. So we've used the T calculator before, stat calculator's T, to find a probability. And we have how many degrees of freedom. Well, let's go back to this. Same thing that we learned before. The degrees of freedom is always the sample size minus 1. So since we have 20 sample size, we have 19 degrees of freedom. So let's type that in. And we want to be less than or equal to negative 0.631. And there we go. 2678 is our probability. And now our conclusion, well, we're going to do the same thing. We just compare this p-value to our alpha. Now, no alpha was given to us, so we can just assume our most common one, again, is 0.05 for our level of significance. So we can just write our sentence. So since our p-value is greater than alpha, it looks like, which is 0.05. Well, if it's greater than, then this is something that's still likely to happen given the null hypothesis is true. So we'll fail to reject the null hypothesis. So we fail to reject H naught. Well, what does this mean for us? Is because we're failing to reject because we don't have enough evidence that it's wrong. So there is insufficient evidence to show the mean running time for the 5K was below 30 minutes. All right, so we see again from our sample, we got a mean that was below 30 minutes, but that's, even though it's some evidence that it is below 30 minutes, it's not enough for us to definitively say at a 0.05 level significance that, yeah, the mean of everyone is below 0.05, or below 30 minutes.